Hi there, I'd like to introduce you to this 8031 computer system that I built, and I built this from scratch. What it was is that I worked with Arduinos and Raspberry Pis, and I really wanted to get down into the machine level with those systems. It's difficult to get to the machine level, so I was looking for something old school. This is an 8-bit 8031. This is the 8031 processor here, so I'll show you around this board here. So this is the 8031 processor. So the 8031 in this design is using a Harvard architecture. That's where the instruction memory is different from the data memory. So they're separated. In a lot of processors, they use von Neumann. Mostly the ones you use on your computer are von Neumann architecture, where the data and instruction memory are shared, but in this case they're separated. It gives it somewhat of an advantage. The nice thing about the system is if you really want to learn computers, this is a good way to go. It's old school and it has basic assembly language instructions, and that's great in that if you can learn this, that was very old, from the 1970s, so the design is over 50 years old. The nice thing about it is that if you learn the instructions, it'll help you with the future processors that we use today. So this is a good way to learn the instruction set and the way that addressing works, indirect, direct, the different types of addressing modes and pointers. The way all that works is very good. So I added a lot of headers here. So these were so I could plug in a logic analyzer or test equipment or other peripherals so we could run things with this. So this monitor, this is a monitor program. These are the ROMs. So this has instruction memory, and each one of these is 2K. So they're not very big, but in this ROM is contained what's called a monitor program, and that's kind of like the operating system that you can write yourself. I actually wrote this, and I have a way of writing that I'll go through. That makes it easy on this system. So in this ROM, it's a 2K 8-bit ROM. It's 2816. It's a double EEPROM, so you could program it electrically erasable PROM. So this has the monitor program, which gives me some utilities that I can use to program this device. And this ROM is a user area ROM. So this ROM is where I could put my programs. It's another 2K ROM. So the programs generally aren't very big on this, although I could probably use more ROM memory but in this design. But for this educational purposes, this is big enough. So over here, this is a 32K by 8-bit RAM. So this is what we call our data RAM here. So this is read and write RAM, static RAM. So this is a 32K, and this is also 32K. So together this is 64Ks of RAM that you could read and write into. Now the ROM you could also read and write into also. So these are 2K. So the 8031 shares its architecture with the 8051, which is a very popular processor. It's still used today, even after 50 years, very reliable type of processor, but this is the original one, and this is a microcontroller. So the nice thing about this is that it has a UART built into it, so that allows me to talk to it. We have a RS-232 interface here that we could talk to this with, and this monitor program provides the communications, exercises the RS-232 part of it, so we could talk to it. So now the nice thing about this is that I could vary the map, the way these ROMs are mapped. So this switch here will actually swap the mapping between this ROM and that ROM, so I could actually program the monitor into here and then swap the two. So that's how I could develop the monitor program for this. So when I do this switch, this is the monitor, and this is where I put my user program. But if the switch is down, then this becomes the monitor, and then I could put my program data in here. So this switch over here swaps the write enable between these two. So with the switch up, it allows me to write into here, into this ROM. With the switch down, then I could write into the other ROM. And this switch here is the write enable. As long as this switch is down, I won't write or overwrite the ROM. But when the switch is up, it does have the capability to overwrite the ROM. So that's kind of like a safety switch to prevent me from overwriting the ROM. But when I'm programming these, I do have to put the switch up. So this is a 373 latch. It's an 8-bit latch that's needed because the way the address and data is shared, the bus is shared between the processor, and this is an LS138, which is a decoder. So this is how I did the address decoding for this for these ROMs here. And this is just an LS0. I needed some a little bit of logic, glue logic, to make this thing work. And this is a Max 233, which is an RS232 converter. So it takes the data from the UART in here and boosts it up so you can read it through an RS232. So I have a reset switch here, and there's also a dip switch. This also has a reswitch. These three switches aren't connected to anything. So it has a crystal here. I believe it's 11.059 megahertz, which is just the right frequency for the 9600 baud rate that this runs at. So we're going to talk about this some more and go into what it takes to make this work. So talk to you soon. So this is the 5-volt power supply, 5-volt DC power supply that I'm using to power the 8031 system. So I have it set on 5 volts, and I actually have it connected with these clips. There's a red clip there and a black clip here. Here's a black clip, here's a red clip, and that runs into, I don't know if you could see it, but it runs into this header that provides the 5-volt power. So this runs off 5-volt power. It's not like a lot of the new logic is 3.2 volts. This is the old style logic that ran at 5 volts. So this is the computer that I have the software hosted. I have an assembler on here. It's called the MetaLink assembler, and we'll look at that some more. I'm going to make everything here open source, so if you wanted to build this, you could also build one to experiment on. And this is a computer that I'm using. It's got Windows 10 Pro, which is a 64-bit Pro computer, and I have this USB, which is a USB to RS232 converter, and we'll go see how that's connected. There's the wire for it, and it's coming up here to this connector. So you could also use a COM port if you have one on your computer. I know these days it's now year 2022. A lot of computers don't have COM ports anymore. That'll work also. So we use TeraTerm to communicate, which also is a modern program. So one of the problems we have, this is old technology, trying to use it with newer computers. This is like it worked great back in when I first designed this in the 1990s. It worked great with the old 8086 type IBM PCs that use DOS. But now we have Windows 10, and it's all 64-bit. So a lot of the software isn't compatible anymore. So that's a real challenge to get the old programs to work with the new computers. So we're going to go look how this is set up and how it works a little bit more. So here's the monitor to the computer that has TeraTerm up, and I'm going to hit a reset switch, and you can see the cursor update on this computer. That's actually the 8031 talking through the serial port to TeraTerm. So I have in the monitor program, I have a little menu. I have to type an N for the menu to come up that has all the commands that I use. So I wanted to show you that, and we're going to dig deeper into this, and I'm making this open source, so if you'd like to design it or get into it, into assembly language programming for an 8031, that's a great project to work on if you're a real good software engineer and you want to learn how machine language instructions. It's a good way to go. So the first thing I want to show you is the TeraTerm setup. So we're going to run TeraTerm, and I'm going to hit a reset just to see the data coming through. So you can see it does respond when I hit a reset. So the setup is in our serial port, we're using COM4, and it could be different depending on your computer. I have a USB to RS-232 converter. So we went 9600 baud rate and 8-bit data, none parity, 1 stop bit, and no flow control. And this transmit delay is 5 milliseconds per character is needed when we do writes, when we load data in. So this is the serial setup, and TeraTerm is in the public domain. You could download that for free. And years ago we had HyperTerm, and Procom is what I used originally on this, and Procom had some nice features in it that they don't have in TeraTerm, so I had to do some adjustments using TeraTerm. So that's our terminal setup for TeraTerm. So the other thing you want to do is this terminal. So we want to make sure this local echo isn't checked, and if you could set everything, your terminal this way, it's a VT100, which is the old deck VT100, and the new line is carriage return. But the main thing is this local echo isn't checked. I think by default TeraTerm has this checked. So we're going to hit OK here. So I'm going to press the N command, which brings up the menu for this, and that's a good test. So these are all the commands that I have in my monitor program, and we'll go through that shortly. So let's look at the read and write to internal RAM. In the 8031, it has 256 internal RAM locations, and these could be used for various things. It's static RAM, so it could be used for temporary memory storage. Also, some of the special function registers and registers within the 8031 use these locations. So let's so one thing that's important is to be on capitals. Some of these commands only work when you're capital, so let's be we have our capital lock on our keyboard. So let's read some internal RAM. So I'll type the R command. So what comes up is it's asking you to put an address. You have to put 2 hexadecimal digits. So let's look at hexadecimal digit 30. So stored inside of static RAM position 30 is 8A. Okay. So let's say we'd like to change that to something else. So then we would use the W command. So we say W. So we type 30. And let's say we want to put the value in. Let's say we want to change that to 00. So now that's set to 00. So let's read memory location of the internal RAM 30 again. So we type a read command. So we type 30. So you see how it's 00 now. So let's write back to 8A. I'm not too sure if that needs to be used for anything right now, but we'll write that back in. So put write 30. And then type 8A. So let's read it back now. So we type read 30. So now it's AA is stored in there. So the address that you put in when you do a read, the first one is 0. So right now at location 0 is 00. And the final location is FF. So that's your 256. So right now that's set to FF. So that's the read and write command, R and W. So now we're going to talk about the O command, which allows us to read the ROM. So our ROM is 2K, and there's an M command that allows you to write the ROM. Right now we're not going to do any writing. I would have to switch to write enable. It also allows you to write to external RAM, but let's just try the O command right now. So for the O command, I type an O, and then I have to type a 4-digit hexadecimal number. So let's say 0000 is 75. So let's get the next address, and I'll type 0001 is 89. So that's an example of reading the ROM. So the ROM is the monitor ROM is 2K, and the user ROM is also 2K. So it ranges from 000 to it's 0000 to 07FF, is the monitor ROM, and the user ROM ranges from 0800 to 0FFF. So that's one way you could read the ROM. So the next command is called the S command, and that displays the special function registers that are built inside the 8031. Now this is a pretty simple processor. It doesn't have too many special function registers, but in the modern processors today, microcontrollers, they have thousands and thousands of these things. So anyway, we'll take a look at what's in, we'll type the S command. So this is what's currently in the special function registers. We have P0's port 0, P1's port 1, and there's port 2 and port 3. So these are, if you read the data books and the documentation for this, these parameters are defined in the documentation, and we'll go through that pretty soon also. So the next command is our B command, and that will allow us to look at a block of 256 bytes of ROM. So we type B, and so it's asking for a block of ROM. It's a 2-digit hexadecimal number, so if we type 00, it gives us the first block. It gives us from 00, address 00 to address FF. So that's a good way to look at a big block of what's stored in the ROM, the 8-bit data that's stored in there. So that's the monitor program. If I wanted to look at the user ROM, it begins at 800, so I type 08. So that's the data. It's actually identical because I have both programs loaded into the same ROMs right now. So anyway, this is how the B command works. The next command provides 128 bytes of internal RAM. So that's the D command. So I type a D, and that gives me the 128 bytes. It's from address 00 to 7F. And that's internal, the static RAM internal to the 8031. So I can see all the data there for that's stored in there. And some of those are also overlap with special function registers. Okay, the next command is the H command, and I'm going to demonstrate that a little bit later. That's used to load a monitor program. So it actually loads the monitor program into the user ROM, not into the monitor ROM, because you need that monitor. You can't load the same ROM that you're running out of. So this is for updating the monitor, where I can actually swap the chips around or program another. If I have another board and I want to make a monitor program, a new monitor program, that's how I go about doing that. So that's the H command. So the C command, it verifies the checksums of the monitor program. So when we use the assembler, it generates a hex file. It's called the old Intel hex file that has been around for a very long time. That's used to load data. So it's a standard hex file, has the checksum at the end. So the C command goes in and verifies, that you loaded the monitor program properly. So we'll demonstrate that also later. The J command will demonstrate that later. That jumps to run the program from the user ROM. So the user ROM starts at org 800 hexadecimal. So when you hit that, it jumps to 800 hexadecimal. So if you have a program loaded in there, it'll run a user program. Okay, so the next command, which we'll demonstrate later, is the E command, and that's to load the hex file for user programs, which also loads into the user ROM. And then there's a K command, which verifies the checksum for the user programs. So the N command, which I'm going to demonstrate now, it just displays this menu as a reminder of what commands we have. We could always modify this monitor program and add more commands, although right now I'm limited to 2K, and almost 2K is being used. I could use more memory. If I had to redesign this, I would add maybe 8K memory, add more memory, so I could have more commands and increase this monitor program. But the way it is now, it's pretty good the way it is now. So it's good for educational purposes only that I'm using this for. Okay, so now we're going to look at the next command. Is the A command, is the read external RAM. And we could write to external RAM by using the M command. Okay, so let's say we want to see what's in the external RAM. The external RAM is 64K by 8 bits, so it has a range. The address range is 000 to FFFF. So let's read, we'll read the top of the RAM. So I type A and I type 0000. So right now there's all zero, it's 00. So let's write to that RAM. So the way we write to that RAM is to type the M command. So let's say I type 0000 and I want to put an FF in there. So now I type the A command to read that. 1, 2, 3, 4. So you see it's FF. Okay, so let's say I want to write to the top of the data RAM. Let's see what's in there now. So I type A. So I type FFFF. So there's FF in there. So let's change that to 00. So I go to type the M command. And I type FFFF. And I type 00. So now let's read that by typing the A command. FFFF. So 00. So that's writing 1 byte at a time into the external data RAM. So the last command I have here is the X command, and that lets me look at a 256 byte of external RAM. So let's try that. So I'm going to type X, and I'm going to type 00. So you could see this FF here. That's what we previously wrote, but this is what's in the external RAM. When I start this up, I don't particularly initialize it to anything, so it goes to wherever it goes to. We could write some software. We could write software to change all those to store data. And so this is when you put 00, it gives you the range of 00 to FF. Now if I went in here and typed X, at the very end I would type FF. So this is at the very end. Remember, at the very end we set FFFF to 00. So that's what's stored in there now. Before it was an FF. So anyway, that's a look at what's stored in the external RAM. So now I want to give you an example of assembling a program that you could load into this device to run as an example. So I'm using this MetaLink assembler that you could get in the public domain. I'm sure there's plenty of others, but this one generates the hex file. And here's the documentation for it. And you could search the internet to find this MetaLink assembler that was developed many years ago. Now the problem I had, it did run okay on Windows 7, but now I have Windows 10. It's a 16-bit program. I have to use Dosbox now, emulator, to make this work. So here's the document. It's a pretty good document that gets into the details, user manual of this on how it works and everything. So that's the manual for it. Okay, so anyway, I have a program here that I'm going to assemble for you as a demonstration. And I have this one. It's called this is the assembly. It's example 1. So you have to be careful with these digits. I think you're not allowed to have more than 7 digits in the old DOS. You can't have more than 7 characters in your name, so you have to be careful with these names. So anyway, I use Notepad++ to edit the assembly listing, and I'm going to open this one and we'll take a look at it with Notepad. So we'll open that one, and so this is an example. So of the assembly listing that I put in. Okay, so what this does is a very simple program, and what it does is so there's some directives here. So it writes some numbers to the RAM. So the location is 30 to 3F. It's going to write 30 to 3F. Okay, so this lets it know that's the 8051 or 8031. And this is the title of our assembly language program. And you can put a date in there, and the width, when you get a listing, it gives you a listing. And this is the hex file that we want to generate. So we want to start at address 800. So you put an org in there. So this is called, I believe it's just called inherit addressing mode. So I want to load 30 into A is accumulator. So 30 gets loaded into A,
and then I move A to memory address 30. That's in the static RAM, and I do that for all these. And at the very end, I jump back to the beginning, which brings me back to the monitor program. So it's a very simple little program here. So this is the listing here that I'm going to run through the assembler, and I'm going to show you how to run this through the assembler next. So to run this through the assembler, I'm going to use Dosbox. When I had Windows 7, I could run it directly on the Windows 7 command line, but I think Microsoft, they took out that capability to run 16-bit programs where you have to load special software now from Microsoft if you want to do that. So I just went to Dosbox to keep things consistent. Maybe Windows 11, they'll take that away. So I don't trust Microsoft all the time. So anyway, I have a DOS directory here. And so what I'm going to do is start up Dosbox. And you could download that. It's in the public domain. It's a pretty good DOS simulator. So the first thing you have to do is make a mount point for the C drive. So I open Dosbox up over here. So I type, the first thing you want to do is type mount C, and then you say C. I have a DOS directory where I'm keeping the Metalink assembler. So I type DOS, okay. So now I want to go to the C drive, so I believe you just type C here. So I'm using some old DOS commands, so dir. So I have a directory here called ml-asm51. That's the directory that the assembler is in. It's actually the same as this path here when you look at it using the Explorer here. But to get to it from DOS, you type cd ml-asm51. I have cap locks on. So now I can see this directory here. There's a lot of stuff in that directory. But anyway, to run the assembler, it's this program. You can see it over here. It's called ASM, I believe it's called ASM51. Maybe sort it by type here. This is an ASM51EXE. So we want to just type ASM51, and then the name of this file is called examp, AXAMP01. I think by default it takes the ASM file, so we'll type that. So it ran that very fast, first pass, second pass, assembly complete, no errors found. So we're going to look at it just generated this. So it generated the hex file and its listing file. So let's take a look at the listing file, and we'll edit that with Notepad. So now it's the same program again. On this side, it's the input. You could actually print this out. It has a format for printing, but you could see the addresses. You could see the address here and the instruction data in here in this column. So this is what's going to get loaded through the hex file. So we'll take a look at the hex file, and we'll look at that. So there's not much in here. I know this has like it starts off a 10. It's like the number 10 means there's like 16 characters. These characters at the end mean is the checksum at the end here. So that's the hex file. Now so I'm going to load this hex file soon. We're going to load this program and run it real soon. So anyway, I used to use Procom, an old IBM 86 PC for this. And Procom was good because you could cut off carriage returns and line feeds that you don't see in text files. But in TeraTerm, you can't do that. So I have to kind of reformat this hex file that would be compatible with TeraTerm. So the way I do it is I select the whole thing here, and well, first thing I want to do is change this into a text file. So I go save as. So I want to save it as example txt. In fact, I'll make it all capital, txt. So I already had one in there, but I'm going to replace it. So that gets rid of some of the smart stuff that Notepad does that sometimes gets in the way. So what we want to do here next is you want to do this ELO conversion. I believe Notepad, not ELO conversion, but blank operations. Okay, so we want to change all our ends of lines to spaces, because Notepad does some smart things that kind of gets in the way. So now it changed all of our end of lines. At the end of the line, there's like a carriage feed line return, which isn't compatible with the monitor, the program that reads the monitor. So anyway, so now the next thing to do is I want to select this whole thing. So I hit Control A, and then I want to do replace. So wherever there's a space, I want to go here. So I'm going to just put a space in there, and I'm replacing it with nothing. So I replaced all with nothing. So it was done in 6 places. So I hit close. So now there's no spaces, just one continuous line here. So there's no carriage returns. If you look at this with the hex editor, there's no carriage returns or feed control or anything like that. It's a pure text file. So we want to save that. So we'll hit save, and we're going to exit out of this. And we're done with our metal. I'll show you what we have to do next. So now we can get out of Dosbox. So we're going to close Dosbox is closed, and we want to move our text file that we just generated that has the new code into the directory that are into the directory that we use with TeraTerm, where it's just a general directory where I keep everything that I'm using to load into this processor. So I want to copy this over to this directory. So I'm just going to say copy here, and I'm going to replace it because I had done this previously. So there's the file that we just generated. This text file, we'll open that real fast just to look at it, so it hasn't changed or anything. Okay, so that's over there now, and so we're going to load this into the memory of the ROM, the user ROM, and try to run this program. Okay, so we'll do that real soon. Okay, so now we're going to program the user ROM with that new program. So the way we do that is we want to use this E command to load that hex file. It's now, of course, it's now a text file, but we're going to do that. So what we have to do is move our write enable switch. So I'm going to move that so I can write into the ROM. So I move that, and so I'm going to use the E command here. So I type in E. So now I'm going to upload the hex file. So I do that by using the send file with TeraTerm. So I do send file, and I want to find the file in that directory, and it's in this directory. So there it is there that we just generated. So I'm going to click on that and hit open. So it's loading that hex file into the processor. So the load's done. So now I want to turn the write enable off so I don't accidentally write into that ROM again. So now I'm going to verify the checksum for the program. So I type a K command. So I'm going to upload the text file again just to verify that it got programmed in properly. So I see good checksum, so it's reading each line. So at the very end I get a good checksum done. If there was a problem there, it would say bad checksum. So anyway, what this program does between static RAM addresses 30 to 3F, it writes 30 to 3F. So let's look at that static RAM right now. We could look at it using the D command, which is 128 bytes of internal RAM. So I'm going to type D. So if you look at D between 30, you can see it in here. There's data in there, but it's all different things. So to run the program, I type a J, and that'll run the program, and it'll change all these. After it runs, that'll be 30. This will be 31 all the way to 30F. So let's go down here. I'm going to hit J and type the J command. So, okay, so the program ran, it went back and restarted the monitor. But let's go look, we'll type the D command again, which will dump the 128 bytes of internal static RAM. So right, you see this 30 now? You see I have 31, 32. So the program ran successfully. It programmed that into the static RAM. So that's a demonstration on how to write assembly language program and run it on this device. I'd like to start by talking about the documentation for the 8031. It was the MCS51 microcontroller. This is a family user's manual that you could download from the internet, and these documents are plentiful and been around for years and years. And this is a big one that goes into the details. This is probably the most important part of this lesson. So there's basically three sections to this. There's the, we'll zoom in here. There's the architectural overview, which would be very important to review. And if you learn this, this will help you with most other microcontrollers and microprocessors. This is at the lowest level, the most basic and type of processor. And from here, you could assimilate to learning other processors. The next part is the instructor's program guide instruction set. So the programmer's guide and instruction set. This has the instruction set for the 8031, which is important to learn these instructions. They're similar even on more modern processors. Today we have the ARM and the x86 and the AMD and Intel, and all of them are pretty much similar the way the instructions work. So if you learn this one, it'll be very easy to assimilate to other ones. And this section, this is the hardware description of, say, the 8051, where 8031 is the ROMless version of the 8051. And this area here, this is basically the data sheets for the part, the component. So we're going to go through this a little bit, and I'll point out some areas that are important. So this is the beginning of the architectural overview for the 8031, and it always starts off with a block diagram of the basic system. If you go to the data sheets, you'll find some more advanced block diagrams. But if you go through this, yeah, it tells you that it has 64K of program memory and 64K of data memory. I guess program memory sometimes we call so-called instruction memory. And there's 4K bytes of on-program memory. That's only for the 8051. The 8031 doesn't have that. It's all external program memory for the 8031. So there's 128 bytes of on-chip data RAM. There's also some higher memory that has a special function registers that go beyond this data RAM area. This is the beginning here, and so if you go through this architectural book, it explains a lot, and this is something that you really need to study. If you study this, you'll know what the processors were back then in the 1970s, but it'll also help you with today's processors. So this is a table, some of the devices. Of course, probably all these are obsolete by now, and it goes through the different types of memory and where things are located in memory. And this is the program status word. That's important to learn. All microcontrollers and microprocessors have something similar to this, where it gives you the status of a logic equation, say, to know if it's true or false. I believe it uses this carry flag in the 8031. And just going through some. Okay, so the addressing modes are very important. You'll find even some more advanced addressing modes in the newer processors, but you'll learn about direct addressing, and that's going directly to the memory. Like you set the accumulator, say, to a memory location, and there's indirect addressing where the memory location has an address that is indirect, that tells you where the data is located. And there's register instructions. That's just miscellaneous type of instructions. Instructions that you process on registers. And another thing is immediate constants. It's loading an immediate into accumulator. And there's also index addressing. So all processors have this indirect. It's called indirect addressing. And then you can have indexed indirect, so where there's an offset. So this has some basic indirect addressing compared to some of the modern processors have even more advanced ways of doing that. So it goes through the different instructions. So these are the basic instructions that every processor has. So if you learn this, it's good to learn in that it will help you. So the next section is this programmer's guide and instruction set. So it goes through every instruction and where things are located in memory. And this is where the special function registers, where they're located in memory. So at that higher address location of static RAM. So there's a memory map here for the special function special function registers, and there are some empty spaces here. I believe you can use as just general RAM if you need to, but these are kind of dedicated for certain purposes. The ones that have values in here. So it goes into the program status word and some of these registers, what these special function registers do. So that's important to study. Depending on what you're doing, you might not need to know all of them, but if depending on what you're doing, you need to know them. So it goes through a summary of the instruction set. So here's the instruction set here, and add is a very common instruction, and it has the different types like the register add, a direct, an indirect, and immediate. So there's add and carry, and this might be considered a complex instruction set. You could actually do bit operations. I think they lost a lot of that in some of the modern processors that you could have done back then that you can't do now. And it talks about how these flags are impacted by by each instruction. So it's nice to look at these. Sometimes with the new processors, they don't give you this information anymore, where it's very difficult to get the moves, the ors, the jumps, pushing the stacks, long jumps and short jumps, and these are operations on the stack if you use subroutines. So they give you, there's a hex code for every instruction, and the way it's used, there's this is like what's in the machine language. So when you do the assembly, it actually generates these hexadecimal numbers that are the instructions that you don't normally have to remember. These you don't have to worry about. But just briefly going through the instruction set. So the nice thing, it goes through these instruction definitions. So for every instruction, it goes into details of what it does for every bit. So it has examples on how it impacts the different bits and how much memory it takes. So there's a register which only takes it's only a 1 byte instruction. Now if you do a direct address, and it takes 2 bytes. So if you do an indirect, it's also that's only a 1 byte add, and then there's a immediate that takes 2 bytes to do an add to the accumulator. So it goes through every instruction in detail. So this is kind of the handbook for every instruction. Hopefully the modern processors have this. They might be much bigger and larger, maybe more instructions. Of course, they went to reduce instruction set processors, and hopefully they have less instructions in this. So then it goes into the data sheets of so when you get to the data sheet part, it's nice. It gives you a better architectural diagram of what's inside, say the 8031. So it shows the special function registers, and it shows these the drivers, and so anyway. So with this project, we're going to go through more examples. Hopefully in the future with this, I'm going to write some different examples using the different addressing modes, and with some interfacing, doing some real-time control with it. And so So thanks for watching this. This is just an example of an old school processor that you might be interested in learning. In that, if you want to learn the modern processors, this is a good place to start. As the modern processors are very complicated, this is a much simpler one to start with, and then you can take it from there and then learn the more complicated processors.